Hello, my name is Lee Babi, and today I'd like to present you our work, Mining Software Repositories, with a collaborative heuristic repository, which we worked on together with Julian Preller, Lawrence Stricker, and John Karmakar, Andrea Yanis, and Roman Hope. We tackled the problem of categorizing software engineering artifacts with the help of heuristics leveraged by weak supervision techniques, and present BOHR, the repository of heuristics and an infrastructure to efficiently gather, integrate, and combine them. A large amount of data is produced as a result of software engineering activities. This data can be used by researchers in the fields of MSR, mining software repositories, to perform empirical studies and train machine learning models to aid software development. Examples of such data include Git commit histories, bug reports, app reviews, Stack Overflow posts, and many others. Researchers are often interested in a certain subset of the data mined from software repositories. For example, studies on fault localization or program repair are interested in the commits that fix defects. Therefore, it's necessary to be able to categorize such artifacts. Performing categorization or labeling manually is precise, but cost inefficient and does not scale well. That's why researchers come up with heuristics for automatic categorization. For the case of commit classification, such heuristic could be, for example, matching the keyword fix. The heuristics, however, are often imprecise, and the resulting data is noisy, which impacts empirical studies based on this data and the quality of the built models. We argue that using heuristics is not the problem. Rather, it is using not enough of them for lack of way to effectively gather, integrate, and combine them. We propose to use weak supervision, whose idea is to leverage large noisy datasets automatically created by a large number of heuristics, instead of small hand-labeled datasets. To implement this approach, we use Snorkel, the state-of-the-art weak supervision tool. Heuristics, or in the terminology of Snorkel, labeling functions, are small subprograms that define rules to determine which label to assign to an artifact based on its properties. They can also use for that the output of external tools, such as already existing low-quality classifiers. Labeling functions have the following important properties. They can have limited coverage on a dataset, in other words, they can abstain on some data points. They can be correlated or conflicting, and of course, by their nature, then they can be imprecise and noisy. So a researcher can think of a large number of heuristics and pass them to Snorkel as labeling functions. Snorkel leverages these labeling functions to learn a generative model of labels. This model then assigns probabilistic labels to previously unlabeled data. To train the label model, Snorkel learns how labeling functions are correlated and estimates their accuracies. Note that it doesn't require previously labeled data as ground truth. The label model can already serve as a classifier, even though one can also use the dataset labeled by the model to train another classifier, a discriminative model that can generalize beyond the heuristics. We evaluate the approach on the task of commit classification and classify commits into corrective or bug fixing and all the others, non-bug fixing. We performed the evaluation on 3 datasets from the previous work, which contain around 1,375 and around 5,000 manually labeled commits respectively. To be precise, the dataset of Heuristic and colleagues is a dataset of manually classified issue reports. We recovered the commits linked to those reports and used the commits as a test set. As a training dataset, we use 200,000 commits mined from GitHub by ourselves, for around 35% of which we recovered links to related issue reports. We principally employed only keyword matching to demonstrate that the approach works even for simple heuristics, provided that we have a large number of them. In total, we have 302 heuristics. Each of them tries to match keywords to either the commit message, the corresponding issue report body, or the issue report labels. We use the commit messages from the commits on which the label model didn't abstain and corresponding labels assigned by it to train an end classifier, which is a 6-layer transformer pre-trained on Stack Overflow posts. We used 2 baselines from the previous work, Tufano and colleagues using 6 keywords to precisely identify bug fixing commits, and Git proc tool, which uses 17 keyword heuristics. We report accuracy, precision, recall, and F1 score, and here you can see the results. Even though the Tufano and colleagues classifier has the highest precision of detecting bug fixing commits, and it was specifically designed to have high precision, our label and transformer models have the highest F1 score, especially on the 2 largest datasets. Moreover, the transformer outperforms the label model on 2 out of 3 datasets, which confirms that the ANT model can be effectively trained on the probabilistic labels. Researchers working on different problems often need to categorize artifacts in the same way. In this case, working on the same pre-processing steps individually is a missed opportunity. Instead of thinking of and implementing the same heuristics by themselves, researchers could contribute them to a shared repository from which everyone, including themselves, could benefit. Maintaining a shared repository, as well as contributing to it and using it, has extra costs. That's why we propose BOHR, Big Old Heuristic Repository, a repository to collect the heuristics, as well as the infrastructure to manage it and make its usage easier. BOHR achieves its goal of facilitating sharing and reusing knowledge in the following ways. It lowers the barrier to contribute by providing a clear API and convenient abstractions for heuristic creation. It automatically evaluates the effectiveness of newly added heuristics by checking if the metrics have improved. This is implemented as a continuous integration pipeline that is triggered by pull requests that contain contribution to heuristics. GitHub bot automatically posts a comment informing whether the metrics have improved, and if so, pull request is merged, and then the set of heuristics is extended. BOHR labels the datasets registered with BOHR and automatically updates the labels when the set of heuristics has changed. We designed BOHR with reproducibility in mind. BOHR keeps tracks of heuristics used for each version of the generated datasets and models and make sure they are easily accessible. To accomplish that, BOHR makes use of DVC, which stands for Data Version Control, tool for versioning datasets and experiment pipelines. On the right-hand side, you can see a few steps needed to retrieve the labeled dataset from the evaluation we demonstrated before. Except for heuristics, BOHR provides some abstractions the user has to interact with when working on a problem. First of all, the user needs to make sure that the needed task is defined in BOHR, or define a new one by specifying a training dataset, a large unlabeled dataset on which the labeled model is trained, a manually labeled test dataset on which the model is evaluated, as well as by defining the set of labels that can be given to data points. For their task, a researcher can use an already registered in BOHR dataset or add one. A dataset can be physically added to BOHR or can be declared as imported, for example from Zenodo. Labels that are used for the task have to be registered or have to be selected from those already registered in BOHR, so that they can be reused across tasks and heuristics. To be able to reduce the labels even more, labels are organized in a hierarchy, so that more general tasks can make use of more specific tasks and heuristics. For example, a task of classifying commits into defect fixing and others can benefit from the heuristics defined for the task of finding commits that fix specifically concurrency bugs. Note that BOHR automatically detects which heuristics need to be run for a certain task. When implementing heuristics, instead of having to manipulate datasets directly, a user can work with artifact abstraction provided by BOHR. When defining heuristics for a certain type of artifact, they can conveniently access all its properties independently of the format in which the dataset is represented. For this to be possible, BOHR implements mappers that map different formats of datasets to different artifact types. Additionally, BOHR provides a way to specify links between datasets, for example, linking commits and bug reports. As a result, a heuristic can access not only the properties of the artifact in question, but also those of the linked artifact. While primary focus of BOHR is on sharing heuristics, infrastructure designed within BOHR allows also sharing knowledge on other levels. Firstly, researchers can reuse datasets labeled by BOHR. Secondly, trained models can be reused to train datasets, to label datasets, not registered in BOHR. Thirdly, the user also might not want to use the model already trained with BOHR, but rather contribute more heuristics to train an improved model. Finally, the task the user works on might not be defined in BOHR, or the definition of the task might differ. In this case, the user would have to define a new task. Some already existing heuristics could be still reused though. Our goal is to make collaboration of the community on software engineering artifact categorization easier. However, this is impossible without the community being involved. Therefore, we invite the community to start using BOHR, reuse already existing labeled datasets and models, contribute to heuristics and improve the quality of existing models, define new tasks. Other than using BOHR, the support with framework development would be invaluable. Please take a look at the BOHR GitHub repository by typing in the link or scanning the QR code. Summing up, we applied weak supervision to label software engineering artifacts. We evaluate our approach on 3 datasets using 2 baselines to show its credibility. Then, we took one step further and implemented an initial version of BOHR, a repository for gathering heuristics to be able to use them across tasks and research groups. Finally, we designed the infrastructure around BOHR to be able to contribute to and use BOHR efficiently. Thank you for your attention.
Okay, welcome back, everybody. This is the third paper in source code history and documentation session. This is a near paper, so a short paper will have 5 minutes for Q&A. I'm here with Lip, who is the author of Mining with a collaborative heuristic repository. If there's already any questions from the audience regarding the work and the tool associated with the work, the website associated with the work, BOHR. Mm, like it, so maybe I can ask you maybe a few questions about the study before getting
Sure.
into the tool, if you want to. You mentioned that you found those three heuristics where you compare with state of the art. Just to clarify, those heuristics manually or were actually the heuristics uh, with the application of the method?
No, it was yeah. Those heuristics were found pretty much manually. These are basically pretty much a list of like keywords that we would match, and also different. Also, we would match bigrams. Also, we would stem some keywords. So each of those things was a heuristic, basically.
Okay. And so my question right now is, how many of those were overlapping with the baseline studies that were based on keywords as well? I guess Tufano et al. Is one of them.
Right. I I wouldn't be 100% precise now, but I think we covered pretty much all the heuristics, all those keywords from that study. Yeah, basically that was the first things we took,
Right.
and then we added more on top.
Right.
Yeah, I think it was it.
So now, if there's no more questions, if there's still no questions from the audience, I'd like to talk about BOHR itself. And just a curiosity, I've seen that you have this small DSL to define heuristics, but do you have also something like that to define new task, or how do you define new task?
The task. So we have basically a so-called BOHR config where we can define the tasks, and basically it's a JSON file where you define the name of the task, the data sets that are used for training, evaluation, and the labels that can be assigned as by the heuristics for this task. So this is defined in a JSON file for now.
I see. Okay. So it's configuration based. I see. Similarly, another curiosity is about the labels. Labels to this hierarchy that you show, or you can create new hierarchy.
Sure. Yeah. So first of all, I should mention that this is pretty much the work in progress now. So when we were working on the paper, we had only two labels, bug fix and non-bug fix. But then we decided to add this additional layer to be able to reuse these heuristics for different tasks without even changing the heuristics. And that's why we started defining this hierarchy. Yeah, this is basically also we have a configuration file where we define that, for example, where we define for example, non-bug fix can be a refactoring, a documentation update, and so on. So yeah, we define it in a text file. And
Thank you so much. I think there's no questions from the audience, but there will be a discussion room opening up soon in less than 10 seconds. So I hope people can join you there, and maybe you can demo some of the features to them. See you.
Sure.
Thanks.
Thank you, Daida. Thank you.